Points on a circle. Pretty much everything we did in the previous sections, distance formula, slope of lines, slope of parallel and perpendicular lines, taking all these things that we know about lines, and then we're going to channel it into points on a circle. So this seems like a very strange process, to be honest. You're always going to have a center point for a circle, and then you're always going to be given a distance for a radius. How long is the radius? What are the coordinates of the radius from the center point? Does a point given lie on the circle? If it doesn't, then no. If it does, then yes, it does. And we can do that by measuring the distance, distance, from the center to the outside of the circle. So if a point is lying on the circle, then that means it's going to be the same distance away from the center as all of the other points on the circle, because the center point of a circle is equidistant from all of the points that make the circle, right? That's what makes a radius. You can spin a radius around like a clock, and it's still going to be the same length of line around the entire circle. That's what makes the circle. So what we're going to be doing, oh geez, look, is that the distance formula again? Yeah, it is. So what we're going to be doing is we're going to be testing the distance from the center to the outside of the circle. And if we're getting the same answers, that means that, yes, they are equidistant from the center. If they're equidistant from the center, then yes, they lie on the circle. So you could, go through the notes if you wanted, but I'm going to go through an example. So XY is the diameter of circle W. So I went ahead and just made a dotted line. It should be a solid line. I just feel more comfortable making dotted lines all the way from X to Y, crossing through the center point W, meaning that if we were to just kind of break this up into a radius right here, that WX, that segment, is going to be equal to WY. So those two sections right there, a radius plus a radius makes a diameter. A radius is going to be equal to another radius to be added to make that diameter. So that's why those two segments are going to be equal. So how long is the radius of circle W? Well, we could go from the length of W to Y, or we could go from W to X. It doesn't really matter. So I'm going to go from, let's go W to X. It seems easy to work with zeros in 3 and 2. So radius W to X. Well, that's going to be, I'm just going to go ahead and label these real quick. X1, Y1, X2, Y2. Okie doke. So now I know that I'm going to be using the distance formula all over again. X2 minus X1 squared plus Y2 minus Y1 squared. So X2 is 3 minus 0 squared plus Y2, 2 minus 0 squared. And this seems like it's a bit easy. So 3 minus 0 is 3. I'm going to square it. Plus 2 minus 0 is 2. I'm going to square it. Square root. That's going to be 9 plus 4, which is going to be the square root of 13. Okay, so cool. All right, so we found the change in y and the change in x. What we did is we created a right triangle using the radius or the line segment xw or wx. So we counted how far over we had to go, how far up we had to go, since it is slanted upwards. So the change in the rise and the run, we're talking about 3 and 2. This again coincides with Pythagorean theorem in that the legs of the right triangle that were formed from that line segment are going to be 3 by 2. That's A and B. And we squared both of those. 3 squared is 9, 2 squared is 4. And then the sum of those is going to be what c squared is, which is going to be the square root of 13. Now, if WZ measures the same thing, the square root of 13, that means that they are the exact distance apart from the center, which means they both lie on the circle. So let's go ahead and test that. So WZ, okay, so Z is right there. So the question was, well, how long is the radius of circle W? Well, square root of 13, okay? So we can go ahead and just put that right over here, square root of 13. Now, the next part is, does 1, 2 times the square root of 3 lie on the circle. Well, I don't know what 2 times square root of 3 is. I guess I could type it in my calculator. It comes out to be like 3.4 something. So it looks like we're going 1 and then 3.4. It might be right here, but we have to test it. We can verify it. So WZ, same process, except I'm using Z now. So I'm going to go X2, Y2. Okay, I'm just going to mark those out, not using those anymore. So that would be y2, which is 2 times square root of 3 minus 0. Those zeros are awesome. And then 1 minus 0. You change it, x squared. Okay, so now we've got 2 times square root of 3 minus 0. Okay, so we're going to square that, plus 1 minus 0 is 1. So 1 squared, square root that whole thing. So to break down 2 times the square root of 3 squared, what's going to end up happening is that square is going to be squared right here on the 2, which is going to be 4. And then you're going to square the square root of 3, which is just going to make it a 3. A square undoes a square root. Cool. So 4 times 3 is going to give you 12. So there is 12 plus 1 squared is 1. Square root. So 12 plus 1 is 13. That matches the same distance as WX. So we know that WX, right here, is the square root of 13. We also know that WZ is going to be the same distance. So we could put Z right here because we know that's where it's at. Z, which means that that is also the square root of 13. So yes, that point does lie on the circle.